Hi, Assalamualaikum. This one is a problem on continuous system, one of the sample final exam or test 3. Basically, in this question, it says the first part is you have to get derive the equation basically, and you can see here formulate the equations. Okay, and it states very clearly on the torsional natural frequencies and mode shapes of the shaft. So basically we need you to derive the equations. The conditions here, both ends are fixed. So this very easy. Both ends fixed means you have to identify or define the boundary conditions as displacement equals to 0. They also give you, of course, some of the parameters that you need to use your dl as the diameter, the g, and the rho standard variables. And in part B, they give you some of the parameters, and they want you to compute on the third torsional natural frequency of the shaft. So once you know the expressions for torsional natural frequencies, so you can actually calculate that. So let us go ahead and derive the part A first, and you can see here I already have it drawn as such, because it says both ends are fixed, so we know that at x equals to 0, so you do need to define where do you define your x. So x, remember, x is the position on the shaft in this case, and your theta is your displacement because it's torsional. Okay, so when it's torsional, your displacement defined as theta. Okay, so do the same thing on the right hand side of the equation, where your x equals to L and your theta is also equals to 0 because both are fixed. So I name it as boundary condition 1 and 2. So we have to write the general equation. So I wrote the general equation here, so don't forget to change from y to theta. Okay, so your theta is the displacement, your x is the position on the shaft. So let us work out what happens if you actually substitute your x equals to 0. So for your x equals to 0, I'm going to go ahead and just write it in terms of x. So if you remember, if you actually divide, because everything is equal to 0, so if you actually divide the terms of t, you do not have to write the t expressions. So then you substitute. So basically here you have a sine. I'm working out from the left hand side, boundary condition 1. So your x is equals to 1, so sine 0, okay, plus b cos 0 equals to 0. Okay, why equals to 0? Because we are using this boundary condition. At x equals to 0, theta equals to 0. So from that, you can know that sine 0 is 0 and cos 0 is 1. So that means so this expression sine 0 is already 0, and you left with your b basically. Cos 0 is 1. So your who gets 0, remember the game is who gets 0. So in this case your b gets 0. Then do the same thing for boundary condition number 2 with x equals to L. Alright, so in this case, since your b is already 0, so the way you write it is you have your theta, so instead of x equals to 0, your x now is equals to L. So you only have the b expressions because you only have your a expressions because your b is equals to 0. Okay, let me just write that down again. So you have your general equation here. You have a sine, so you have omega over c. Your x is equals to L. Okay, then you have, since your b equals 0, Okay, so just 0 there is equals to 0. So from there you can see, since b equals to 0, so your a cannot be equal to 0, because if both of them are 0, that means there is no vibration. So now we want to compute the vibration. So a cannot be equal to 0. If k cannot be equal to 0, so what is 0 is basically your sine omega over CL is equal to 0. So if you look at these expressions, sine inverse of 0 is basically omega CL is equals to sine inverse of 0, yeah, which is equals to the multiple of your pi. Okay, pi, 2 pi, 3 pi. Why we have a series here? Because continuous system means the system is continuous, means it goes to infinity. So I can write as n pi. Okay, you write it in terms of series. So how do you, from here you can actually get your omega n. Okay, omega n here is actually the natural frequencies, where you express it in terms of series. So you rearrange the terms, you have n pi, so you bring the c over L to the other side of the equation, so you will get your natural frequencies. So this is the expressions, okay, where you can also define your C, because they want you to write it in terms of density. This is a torsional this is a torsional system, so they ask you to write it in terms of G and rho, G over rho, meter per second. Okay, because C is a velocity. Okay, so that is the answer for your natural frequency. Okay, then they ask you to get the mode shapes. So how do you actually define the mode shapes? Is you go back to the general equation. Okay, from the general equation you can write your mode shapes. We know that your b is equal to 0, so your mode shape you just write back from the general equation with your b is equal to 0. So the way to write your mode shape, okay, maybe I put it in terms of capital theta, because it's mode shape is equals to, we can just put any constant in front instead of a, okay, for a mode shape. Sine, so it has to be omega n over cx. So that's how you do it. You just take the expressions for the a term, because b is equal to 0. Okay, so now instead of a, you put just any constant, yeah, for the mode shape. So what you need to do is you substitute your omega n. So sine, so substitute your omega n here. So you put your n pi c over L. So then you have to times again your c, then your x. So you can see that you can cancel that out. So your final mode shape equation is basically Cn sine n pi x L. Alright, so this is the final answer for your mode shape. So we've done with part A basically. So now we want to take a look at the part B. Part B, they ask you to actually they give you all the parameters, the diameter, and then the shear mode, the G, and also the rho. Okay, so they give you also the third value. So you are what you need to do is you need to use the equation for the third natural frequency, and they give you the value of the third natural frequency, and they want you to calculate the length. So it's easy. So you already have this equation, so you just substitute for the third natural frequency. Okay, and then you just compute the L. So for the third natural frequency we have found just now, the general equation is n pi. The general equation is n pi c over L. So now if it's the third natural frequency, it's just 3 pi c over L. So they give you 5,000 for that, and then your c is square root of g. So they give you the g value and the rho value. So what you need to do is just you solve for your L. So if you do that, basically your L is equals to 3 pi over 5,000. Okay, and then you have to compute your g, your c, basically your square root of g over rho. If you calculate that, you should get 6.02 meter. So this is the final answer for B. Okay, so that's all for this whole problem. I think it's very easy peasy. You just need to know to derive the equation for the torsional vibration, given the boundary conditions, get the natural frequency and mode shapes, and then you have your condition. So this part B is always a condition, substituting values and solve for the conditions, in this case solving for the length. Okay, that's all. Thank you.